So let's take a look at this problem. A hydroelectric power plant receives 10 meter cube per minute of water from a dam where the water level is 75 meters above the turbine discharge water level. So here's our dam. And we have water backed up, and it's going to discharge on this side, and that elevation difference between the water on the dam side is 75 meters above the discharge. So we have a hydraulic turbine which will take some water in and discharge it. Now that turbine is used to generate electricity. So what does the output of that hydraulic turbine is to turn a shaft which is connected to a generator which produces electricity. And so the overall turbine generator efficiency is 82%. Well, we use some symbol for efficiency, maybe eta, and it's 82%, but well, what exactly is it? Well, you're getting energy out of the fluid stream. Let's talk about the power that is in the fluid stream that's going to come out. If the turbine was 100% efficient, it would convert that to the power in the rotating shaft. And if the electric generator was 100% efficient, it would convert it all into W dot electric. But it's described to have a turbine generator efficiency of 82%, and that turbine generator efficiency is how much gets eventually to where we want it to get to. We sell electric power compared to what it comes out of the fluid stream. This W dot fluid, you can think of it in three ways. Okay, it would be something like the energy per unit volume times the volume per unit time flowing. True? So if I made the product there, I say the change in mechanical energy of the fluid divided by, well, per unit volume of the fluid times the volume per unit time that the fluid flows through the hydraulic turbine, then I would get what is coming out of the fluid stream. You could also write it as energy per unit mass times the mass per unit time of the fluid. What's the change in the mechanical energy of the fluid per unit mass of the fluid times the mass flow rate of the fluid? You could also write it as, this one won't make much sense, but you could write it that way, energy per unit weight of the fluid times the weight per unit time of the fluid flowing through the device. So you could write it either one of those three ways. This is where change in mechanical energy per unit volume is the pressure. So what is the change in the pressure across? What is the change in the pressure across the hydraulic turbine times the volumetric flow rate AV? What is the change in the energy per unit mass, something like a cap H for head? I don't think the book uses cap H for head when it's energy per unit mass, but I like to, times m dot, or energy per unit weight. Oh, that's the change in the elevation, the change in the head across that, so it's really a change in this as well, times the weight flow rate. Well, I don't have a great symbol for that, but it would be something like, well, let me just, I don't have a symbol for the weight flow rate. It doesn't make much sense. I have mass flow rate, and then if I multiply the mass times G, we recall that weight is equal to mg, so g is the weight per unit mass. So if I multiply mass flow rate times g, I'll get weight flow rate. So one of these forms is the most useful to calculate what is coming out of that fluid stream. And then if we multiply it by the efficiency, you'll get what is actually able to be generated in electric power. Does all that make sense? So now I give you a few seconds to pick your answer, A, B, C, D, or E. Okay? So solve this problem. And we're there. Okay? Hopefully everybody got in a vote. Let's break this down. We want to calculate, what do we want to calculate? The electric power generated. That's W dot ELEC in my notation. And that would be the overall turbine generator efficiency times the power that could be maximally extracted out of that fluid stream, which is can be described a number of different ways. I look at the information given. What is this information? 10 meters cubed per minute. Is that a mass flow rate, a weight flow rate, a volumetric flow rate? Yeah, it's a volumetric flow rate. So I can say the volumetric flow rate, AV, is 10 meters cubed per minute. If I knew the change in the pressure across, then this would be really straightforward. If maybe I can use that to get the mass flow rate, is just rho AV. So I could come down to one of these forms, which would be also very convenient to use. So it looks like I multiplied by 1,000, so it's 10,000 kilograms per minute. That's the mass flow rate, true? Because the density of water is 1,000 kilograms per cubic meter. Then I look here and I say, if I want the W dot of the fluid, it'll be the change in the head, thinking about elevation, because that's what they gave us right here. You can use it H or delta H. It's the elevation difference between the inlet and outlet, multiplied by the rho AV. And so this is 75 meters times 10,000 kilograms per 60 seconds. And I'll just go ahead and a kilogram meter. I left out the G. See that G? I left out the G. Sorry. So it's taken me some time to realize I needed that G. 9.81 meter per second squared. I think that's an example where if you're chasing your units, that's my way of saying check your units. Sometimes it'll stop you and say, hey, I've got a problem. That's what I just did. And I need to back up and figure it out. So now I have a kilogram meter per second squared. That's a Newton. Multiply that by a meter. That's a joule. Divide by a second. That's a watt. That's a watt. So when we run this, what do you get for this? 75 times 10,000 divided by 60 times whatever it is. We have 122,625 watts. True? That's what, if you had everything maximally efficient, you can convert all of that fluid power into electric power. That's what you'd have. Let's go ahead and convert that to 122.625 kilowatts. And then if we want the W dot electric, multiply that by the 82%, 0.82, 122.625 kilowatts. And what do we get? Right at 100 kilowatts. So what's the best answer? How many people were able to get that one? Pretty good. Did you use a different thought process, a different way of navigating the algebra to calculate it? You did pretty good. This is a problem where we want to calculate the maximum height that a water stream can be issued to. So you have water, it's sealed in a tank. The air is on top of the tank, and it's at a gauge pressure of 90 kilopascal. And the water level in the tank's 8 meters. And the question is, what is the maximum height, h, that the water could reach if it's extracted from the tank at the bottom in this hose and then goes over to a nozzle and then shoots up? Well, we would use the Bernoulli's equation. We'd put state maybe 1 here, and you'd put it all the way through and go to the end. For discussion purposes, maybe we'll have a state 2 here, and maybe a state 3 here, and maybe a state 4 here. You don't have to always go 1 to 2. You can go 1 to 4. Well, when it's at the maximum, what is the velocity at 4? 0. Now, what also is the velocity at 1? Because a large tank, it's approximately 0. It's not precisely 0, but we're getting an estimate of the maximum height that the water could be shot to. If there's any friction in viscosity effects, it will reduce that maximum height. We'll use Bernoulli's equation, assuming the conservation of mechanical forms of energy, to calculate that maximum possible height. True? So what we do is we go and apply Bernoulli's from 1 to 4. So we can write it as P1 plus 1/2 rho V1 squared plus rho G Z1 equal to P2 plus 1/2 rho V2 squared plus rho G Z2, correct? And then let's go ahead and strike the kinetic energies on both of those at 1 and 2. And then let's talk a little about the pressure at 1. What is the pressure at 1? It's 90 kilopascal gauge, right? What about the pressure at 4? The pressure at 4. 0 kilopascal gauge. So the pressure at 4, why did I write 2? I should have written 4. Okay. So the pressure at 4 is 0. And now you take a look, and we can solve for that maximum height, Z4, which is, in this illustration, we're going to start measuring elevations from the base, because that's where they measure the water level coming up. So Z1 is equal to 8 meters, and the height which we're looking for is Z4. Z4 is equal to H. So I can rewrite this equation that the unknown height that I'm looking to calculate is equal to P1 divided by rho G plus Z1. And we can substitute numbers. So the pressure, gauge pressure at 1 is 90 kilopascal divided by rho G, 9.81 kilonewton per meter cubed. Did I do the rho G right? 9.81 kilonewton per meter cubed. Let's do our units right away. A Pascal is a Newton per meter squared, true or false? So the Pascal goes, the Newton goes, the kilos go, and we're left with 1 meter on that term. Okay, finishing the equation, we add Z1, which was 8 meters. So 90 divided by 9.81, 9 point something. So that's 9.17 plus 8 is 17.17 meters. And we look, what's the best answer? 17. Okay? All right. Here's a question. This was the problem we just solved. Here's a different problem. But what we did was we took the top off of the tank so the air is not pressurized on the tank. If you didn't have this pump, then the water level wouldn't shoot as high. The maximum height of the water level would be right at 8 meters, true? But somebody says, I want you to add a pump, and that pump is going to run such there's a pressure increase across the pump of 90 kilopascal. That was the same as the air pressure above. If it's 90 kilopascal pressure increase caused by the pump, what will be that maximum height? We did calculate it to be around 17 meters before. What do you think it's going to be for the new case? 17 meters. And so now that really leads us to a change in the Bernoulli's equation, a modification of the Bernoulli's equation, so that we could maybe include gains of mechanical energy due to pumps or other devices that add it into the equation. So before we ran equation from here to there, from maybe state 1 to state 4. Here we're going to run it 1 to 4, but that 1 to 4 goes through this pump. And when it goes through the pump, maybe you come down here and you put that as state 2 and that as state 3. There's going to be a boost in pressure from 2 to 3 without a change in the kinetic energy, without a change in the potential energy or elevation. The pump just has a pressure gain across it. And so, or a head gain across it. So what we can do is we can modify Bernoulli's equation. Let's say somebody says also, I have a model for how I can account for some frictional losses right in here. I can have an equation for the pressure loss due to this bend or this elbow turning or trying to get the flow to start into a tank or into a pipe from a large tank. We'll get those loss coefficients and ways to express that later, but not this chapter. But it gives us the mechanism by which we can either have a gain or a loss. A gain in what? Or a loss in what? Well, energy per unit volume, pressure, energy per unit mass, some sort of cap H head, or energy per unit weight, lowercase h head. This is the more preferred common head. This is a looser definition of head. Okay? Well, this is the modified Bernoulli's equation. What do we have? We have the equation just like we had before. Those are the same. But this is new, and this is new, and this is new, and that's new. All right, so what we have is for flow in a pipe or a duct, some sort of enclosed where the fluid is flowing, we have alpha, and alpha was the kinetic energy correction factor. In almost all cases, alpha is 1. But if you want to be a purist and really detailed, you can calculate alpha. And the alpha equation was something like 1 over area integral across the area of the V divided by V average cubed. True? Well, you don't have to memorize that equation. Isn't that equation on the equation sheet? Can anybody verify the equation for alpha? Find it in your textbook or equation sheet. Is this correct? We have one verification. Good. What equation number is it? Oh, it doesn't have a number? Numberless. What page was it on? Sheet?
On page 229.
All right, so page 229.
Yeah, it's in the chapter summary towards the end there.
And it is in the equation sheet. So that's what that alpha is. And thankfully, it's almost always 1, and you can assume it's 1, and often we're neglecting viscosity and frictional effects. Hence, it's going to be in the noise. But this is your pressure gain or your pressure loss due to some restriction or something that's creating that loss. If it's a gain, it's typically due to a pump, some device that's putting mechanical energy into the flowing fluid. Here's the equation written in energy per unit mass terms, the same alpha. Let's not talk about the alphas anymore. Let's just say you have a cap H gain or a cap H loss, energy per unit mass gain or energy per unit mass loss. Or what's very common is talk about the head gain and the head loss. And later we'll talk too about pumps and everything else, and they'll use the term head and they'll say, oh, the head loss is so many Pascal. Time out. I learned Pascal is pressure. I learned head as some sort of lowercase h, which is elevation. When you get out in the real world, you have to look exactly, you have to interpret what they're telling you. Okay, they know what they're talking about, the pump manufacturers, but they'll describe a head in units of pressure. Okay, all right. So there you go. So this is put on the gain side or on the loss side. Here's a problem. Water flows at 25 liters per second. What is that, 25 liters per second? It's a volumetric flow rate, isn't it? 25 liters per second. How many meters cubed per second is that? Is it 0.25, 0.025? How many? Is that correct? 0.025 cubic meters per second. It's water. You know what? I can calculate the mass flow rate. Rho AV. I just multiplied by 1,000. Is it 25 kilograms per second? Is that the mass flow rate? Okay, good. We've got the mass flow rate if we need it. If through a valve, 3 centimeter diameter pipe, okay, the pressure drop across the valve is 2 kilopascal. So that would be like a delta P loss. It's a drop, it's a loss. What is the head loss for the valve in units of meter? So, well, let's first calculate the delta P loss. What is the pressure loss? It's 2 kilopascal, that's given. I want to calculate the head loss. What is the relationship between delta P loss and head loss? Is that the right relationship? Think again, what is pressure? Energy per unit volume. And if I had the weight per unit volume, then I could convert that energy to per unit weight, and that's exactly what the head lowercase h is. And so what is rho g? Weight density, or weight per unit volume. So we have 2 kilopascal divided by the density, 9.81 kilonewton per cubic meter. The Pascal is a Newton per meter squared. We've done this before, and we see that the kilos go, the newtons go, the pascals go, and everything but one of the meters go. So it's 2 divided by 9.81. looks like the head loss is a whopping 0.204 meters. True? What is the pumping power that a pump must provide into the system to overcome the valve loss? Think about the water goes in a loop. There's a pump right there, and right over here is my restriction, which causes a loss, and that's the only place there's a loss. So the pump has to put in enough mechanical power to overcome what the valve takes out as the fluid flows through it. M dot or AV. Okay, so what is the pumping power that the pump must provide? W dot pump equal to W dot into the fluid, which you could do three ways. Delta P times AV, delta H times M dot, or delta lowercase h times rho, G M dot. I don't have a symbol for weight flow rate. True. So, which form do you want to use? Which form do you want to, since we already have the pressure drop, that has to be the same as the pressure gain, and we get the volumetric flow rate, let's use that form. So it's the W dot in the pump that has to be provided is equal to the 2 kilopascal times 0.025 meters cubed per second. And then, depending on how you recall unit conversions, a kilopascal times a meter cubed is precisely a kilojoule. True? And so we can get rid of the kilopascals and meter cubed, and we calculate it's 0.05 kilowatts. Can you solve problems like that, like the back of your hand, without any error? Please, please, please work at it, right? Because on the exam, it'll be like, it's so easy. The answer, all I have to do is take this number, which is given, and that number is given, multiply them. It's like, yeah. But please do it correctly on the exam. All right, I know that we covered a lot of material, but we're finished with this chapter. I'm going to go ahead and shut it down and save it, and then we'll move into the next chapter, okay? If you need to take a break for whatever reason, it's a good time now.